So this video is all about similarity as it relates to a particular characteristic of right triangles. Now this video is a little bit different than others in that I'm not going to ask you to do any example problems at the end because we're going to see the real power of the idea that comes up in this video when we apply it to particular practice problems, which we're going to do a little bit later. So first, a reminder that similarity as far as figures are concerned is that two or more figures are considered similar if their corresponding angles are the same size, meaning they're congruent, and their corresponding sides are proportional. Now, for figures larger than triangles, there are a lot of things that we have to check the boxes for. We have to check the boxes that the corresponding angles are congruent. Then we also have to check for corresponding sides. But remember, when we're talking about similarity with triangles, it is enough for us to verify that the angles are congruent. And that sits for triangles and for triangles only. So if we look in particular at this right triangle, there's a particular method that we can go through to find some really helpful, really powerful ratios for similar triangles. And what that has to do with is drawing an altitude from the hypotenuse, or from the right angle to the hypotenuse. So in order to see that, it's not perfectly straight there, so I'll keep working on it for a second. But so in order to see that, we're going to flip this triangle around so that the right angle is now vertically above the hypotenuse, and the hypotenuse is horizontal according to our viewing of it. And then an altitude, you'll remember, is a perpendicular segment that goes from a vertex towards and the direction of the opposite side. Sometimes it intersects the side, but sometimes it doesn't. And so we're going to go ahead and draw that altitude here. And I'll actually move that now so it's above the vertex. And so now we have some new triangles. We have our original triangle, which we could call A, not what I wanted to do, which we can call A, B, C. And now we have the intersection of this altitude that goes from C, which we'll call point D. Now, a few things to recognize here. CD is perpendicular to AB because that's part of the definition of an altitude. And we know that angle ACB is also a right angle. So this actually gives us a series of right triangles. And if we start keeping track of the angles, we can see that they're all of them, in fact, are similar. So angle A, for example, we will color in purple. Angle B, we will color in green, and the right angles will stay as right angles. So those are the angles of the original right triangle ABC. And if we look now at triangle ACD, we can see that it has two angles that we know of. It has the right angle in red, and it has angle A in purple. That means if all of the angles add up to 180 degrees, the same way that they do for triangle ABC, where the angles are purple, green, and red, the remaining angle, angle ACD, must also be green. Because if, for example, D is 90 degrees and A is 30 degrees, the only size angle that can complete a 180-degree triangle is a 60-degree angle. And since angle B would be 60 degrees, and then angle ACD would have to be 60 degrees, we have those two angles are congruent, which means that the angles of triangle ACB are congruent to the angles of triangle, let's see, get this orientation here right. We need to go down the long and the short side. So orientation of angle ADC. So ACB on the big triangle and ADC, their angles are congruent, so they are similar. In a similar fashion, if we look at triangle BDC, we can see that it has a right angle and a green angle. Now, for the same reason that we saw before, if, for example, that green angle is 60 degrees, the right angle is 90, the only size angle that can finish the 180-degree triangle in that example would be 30. But in the broad case, if it has a 90-degree angle and that same green angle that the major big triangle does, ACB, then the only thing that's left is for this smaller angle to be the same as the purple angle. And so we have a series of similar triangles. And we can see that if ACB is congruent to ADC because they have the same angles, that not only are those two triangles congruent, but in the small triangle there, triangle CDB, we can also say that that is similar to ADC because we have all of these congruent angles. And this is what we want to notice about drawing an altitude from a right triangle, or from the right angle to the hypotenuse of a right triangle. And so this is a very powerful theorem with a lot of consequences. So go ahead, pause the video. I'm going to ask you to write down not just the theorem, but also draw the figure so that you know what each of the triangles actually mean. And then next time we talk about right triangles, we will see some of the implications. It relates back to geometric means and ways of calculating the lengths of altitudes of triangles and different various sides. So pause the video before this video ends, write down this theorem, draw the figure so that you know what we're talking about, and then we will continue this at a later time.